Hi there, my name is Belinda Rich. I work in ESA's Advanced Concepts team, focusing on advanced materials for space habitats, and I'm here to talk to you today all about the Advanced Concepts team. So the Advanced Concepts team, or the ACT as we like to call it, is ESA's team of future concepts researchers, and that means we focus on new concepts that could be applied to solving problems in the space sector many decades from now. Our job is to both monitor the current research and perform new research that could either be in space concepts that are too distant in the future for ESA to be focusing on right now, or in topic areas that don't currently have a link to the space sector but have the potential to be. What makes our team unusual is that we are made up of scientists from many different scientific backgrounds. So, for example, currently we have computer scientists, mathematicians, architects, physicists, biomedical engineers, mechanical engineers, and more in our team. Because the ACT is made up of a team of very diverse scientific backgrounds, we are never focused on just one topic. Instead, we are always running multiple studies and projects at the same time. Some of these research projects may look a little different depending on the topic itself. So some of the research will be performed in a laboratory. Some of the research may be testing concepts in a computer model or a simulation. And also sometimes we like to work with universities or research centres from all around Europe to draw on expertise from outside ESA as well. But always we are exploring how our ideas can be adapted to a space context. And sometimes that can happen in very surprising or unexpected ways. For example, an ACT study that I am currently involved with is investigating how we can best build structures on the moon using geopolymer, which is a concrete-like material that uses lunar dust as its main ingredient. In the study, we found that adding urea from astronaut urine to our recipe greatly reduces the amount of water we need in our recipe. And that's an example of how sometimes a great solution can come from an unusual or an unexpected place. A really exciting thing about the ACT is that a lot of the topics we focus on might not be what you expect from a space agency. For example, some of our team investigate technologies inspired by nature or biological process, and this is a topic called biomimetics. Inspiration from nature can come from the smallest places. One ACT project is investigating how plankton in the ocean use nano-sized light-trapping structures to increase how much sunlight they can absorb. The same idea could potentially be recreated to increase the efficiency of solar panels on our spacecraft. Another biomimetics project is simulating the movement of aquatic animals like fish to see how a robot might copy that movement to move through a liquid using as little energy as possible, which could come in very handy for future robotic exploration, with the possibility of liquid oceans in our solar system, for example, maybe on the moons of Jupiter and Saturn. Moving away from the natural world and towards the digital world, the ACT has also been investigating artificial intelligence by training simplified brain models known as neural networks to perform certain tasks. Using these networks, ACT researchers have been able to teach a drone how to pilot itself to a given location in the most efficient way possible. And this means that spacecraft like satellites could use artificial intelligence in the future to navigate, despite their very small computing power. But another ACT study is investigating how we can process lunar dust to create thin structural fibres known as lunar basal fibre. These fibres have the potential to be manufactured in space without any humans present. Then, robotic winding machines can be used to build vast structures out of these fibres by winding a fibrous shell that could be large enough to fit a habitat or another structure. And this concept shows how robots could potentially build on the moon with no humans present at all, and without needing to send any resources to the moon from Earth. We even delve into concepts in fundamental physics and quantum field theory, where the ACT researchers have applied a technique called time frequency analysis, a concept which is already used in signal processing, which is important for satellites, to give a new picture of particle detection in a vacuum. This novel technique represents particle detection using time on the x-axis and frequency on the y-axis, which is quite similar to how you represent musical notes on a musical score. With this technique, instead of helping us to write a song, it's helping us to understand the behaviour of the universe's fundamental particles. These are just a few examples of our recent research, but the ACT also investigates topics in mission analysis, neuroscience, energy systems, advanced materials, and even more. The Advanced Concepts team provides ESA with the capacity to always be exploring potential space benefits of advances made in science and technology. But one thing all ACT projects have in common is that they deliberately look outside the scope of ESA's usual work. While our job in the ACT is not to predict the future, we are helping to prepare and enable lots of potential futures for ESA and the European space sector. And it's those future technologies a few decades from now that our young people today will be using to push the boundaries of space.